In today's linear algebra video, we're going to be taking a look at the identity matrix. What we're going to do is go over a little bit of background behind it, as well as some of the properties like multiplication, the determinant, as well as the inverse and eigenvalues. And then what we'll do is we'll jump into some Python code with the help of NumPy and make our lives way easier with any of these type of calculations. So first, a little bit about the background. Let's look at some information on the identity matrix. So first, the identity matrix is also known as the unit matrix. Personally, I prefer the term identity matrix, but some people use unit matrix. So if you ever see that out there in the wild, they mean the same exact thing. It's a square matrix with ones on the left or right diagonal and zeros everywhere else. So just very two common examples. A 2x2 matrix, right? You can see from left to right, we have ones, and then everywhere else is zeros. On this 3x3, 1, 1, 1, 0, 0, 0, 0, 0, 0. This can get greatly expanded out, but for slide purposes, I'm showing you the 2x2 and 3x3. Remember, identity matrix has to be a square. All right, so what you'll see also, and I probably should have put in the first slide, is the identity matrix is going to be identified by I. Pretty self-explanatory, but let's jump into the first property of the identity matrix. We can have a matrix which we'll call A. A times I is going to be equal to A. Or we could have I times A, and that is also still going to be equal to A, which is our matrix that we define. This would be like multiplying by 1 with scalars, right? So if you say, for example, 5 times 1, well, that's 5. Or 1 times 5, that's still equal to 5. Remember, identity matrix, right? All ones and zeros across the board, ones with the diagonal, 0 everywhere else. So we essentially treat it like 1. So to show you the math behind this, I have this over here, this 2x2, 2, 5, 3, 1. We're going to multiply it by this 2x2 identity matrix, 1, 0, 0, 1. I have the math down there for A11, A12, 21, 22, and you'll see it's 2, 5, 3, 1. Now, if we go the other way, right? 1, 0, 0, 1, 2, 5, 3, 1. You'll see once again, the math behind it is going to be 2, 5, 3, 1. And just to show you again how we find these, right? We take this row, multiply it by this column, this row, that column. We take this row, column, row, column. That's how we do matrix multiplication. I have another video matrix multiplication. I explain a lot more in depth. I expect you have a little bit of a background behind it. So again, how this is mapped out with down below, A11, right? Row 1, column 1, row 1, column 2, row 2, column 1, right? Row 2, column 2. And you can see it is 2, 5, 3, 1, which go back to both of our examples. That was our matrix A. So it didn't matter that we multiplied the identity matrix first or second, we got the same result in the end. Now the determinant of identity matrix is going to always be equal to 1. Determinant is super easy to multiply in this one, right? 1 times 1 minus 0 times 0. Well, that's 1 minus 0. And our answer is going to be 1. The inverse of identity matrix is going to be equal to the identity matrix. So the formula behind it is 1 divided by the determinant times, and you rearrange your matrix, right? So typically you would have A, B, C, D. Well, in the inverse, right, we flip A and D, and then we negate B and C. All right, so now I wanted to show you guys the eigenvalue side of things, right? So the eigenvalue is going to be equal to 1 in the identity matrix. So I have this formula over here. The determinant I minus eigenvalue I is going to be equal to 0. So just to show you the math behind it, right? Identity matrix, eigenvalue, identity matrix. Then I just multiplied the eigenvalue over here, and then we subtract it, right? We have 1 minus the eigenvalue. Others are 0, 1 minus the eigenvalue. And that's how we get this value over here. Then we just find the determinant, right? I've probably done the determinant a lot of times. I'll multiply the diagonals, subtract the other diagonals. Well, you have 1 minus eigenvalue, 1 minus eigenvalue equals 0. And well, the solution is going to be 1. And just to talk a little bit about the data science side of things, well, identity matrices are really good at solving linear systems, helps with matrix inversion, also eigenvalue problems. And, you can see this in the principal component analysis, ridge regression, as well as neural networks. So that's the background behind the identity matrix. Let's jump into some code. All right, let's get started. This is going to emulate essentially what we did in the slides, but with Python code. So we'll start off with importing numpy as np. Throw that in here, and we're off to the races. Now, first thing we want to do is we're going to say example 1. We're going to create a 3x3 matrix. And I'm going to show you 2 different ways that you could generate this with numpy. So the first side of things, we'll say I equals np.identity. Now, this is the way I prefer it. So identity like that. And since it's a square matrix, all we have to do is pass in one value, right? Because it's going to be the same on both sides. I'm just going to pass in 3 over here, and that will print our 3x3. Now, I will show you also the second way, and then we'll print these out. So I'm just going to call this I2, and we're going to say this is equal to np.I, no pun intended, right? EYE. And then pass in 3. Now, this is probably a little bit faster to write than identity, but to me, I'd rather just have identity in here. So just like from the readability side of things, I know exactly what is happening. So what we'll want to do now is print out both of these. So first we'll print out I, and over here, you can see 1 0 0 0 1 0 0 0 1, which lines up with what I showed you a little bit earlier, right? 1's on the diagonals and 0 everywhere else. I shouldn't say all the diagonals, just that one over here going from left to right. So now what we want to do is print out I2, just to show you that both ways work, right? And again, if you prefer that method, awesome. If you prefer using identity, great. Whatever works for you, right? And you can see 1 1 1 0 0 0 0 0 0, same exact results. And literally just one line of code, we can generate that identity matrix. Now, let's go through the matrix multiplication. So example 2, say matrix multiplication, right? And we'll change this up. We'll go back to 2 by 2. And first we're going to say is let's find our matrix A. So we're going to say this is A is equal to np.array. And inside over here, we'll have our values. And when you go and use np array, you define one row at a time. So our top row, let's say we have the values of 2 and 5. And then our second row will have the values of 6 and, 8. There we go. So we have that now. And just to show you what A looks like, I'll print out A. Nothing too special, right? 2 5 6 8. As I mentioned, row 1, then we have row 2 over here. That's just how you define that in NumPy. Okay, so now we want to multiply this with our identity matrix. So we have to set a brand new identity matrix because we can't use the 3 by 3, right? You can't multiply those together. So I'm just going to say I equals np.identity, and we'll pass in 2, right? And again, just to show you what this looks like, prints out our I, right? Very basic 1 1 0 0. Now let's multiply these together. So we'll say result equals np.dot, and then pass in A and I. And this is the order that you are multiplying this in. Now, I showed you in the slides that the order does not matter. I will prove that to you here as well. So we have our result here. And then what I want to do is we're going to do result 2. And we'll have result 2, and we'll have I, and then we'll have A over here. And let's print out both of these so you can see that they are the same. So first we're going to do is present result. And I said present, I meant to say print, but 2568, you can see same 2568, great. And now let's print out our result 2. So result 2, and you can see 2568, same exact results. The order did not matter. We have AI, and then we have IA. Awesome. Now let's go through the determinant. The next few examples are going to be really, really easy, right? So say example 3 is determinant. And all we have to do on this side of things is say, well, determinant of I equals NP, and then I would say linalg, like this. And then we're going to look for determinant, which is .det. and then pass in our I value. And then all we have to do is print this out, and let's get our singular 1 answer. Boom, 1.0, our determinant. And I have a full video coming out pretty soon, or it's already out on the determinant, so make sure to check that out. Really everything in this video I have videos on. I'll have one on matrix multiplication, determinant, and then also inverse and eigenvalues. So awesome, we have that one working. Next, what we want to do is take a look at the inverse. So over here, and we'll look at example 4, which is our inverse. And all we're going to do is say inverse I equals np.linalg inverse, and then pass in I like that, right? And I do have an error, so let me just double check what I had over here. Linalg, misspelled it. There we go. I don't know how I spelled it, but I thought I put linalg like that. Regardless, if we print this out of inverse of I, right, we'll get the same exact results. And you can see 1, 0, 0, 1, because the inverse is going to be the same on this side of things. So awesome. Let's move into example 5, right? Pretty self-explanatory after I showed you on the slides the math behind it. This is going to be our last example on the coding side of things, and this is just going to be eigenvalues. So eigenvalues, right? And eigenvalues like this, right? And this is going to be equal to np.linalg, pass in eig, and then pass in our I. And man, I did that twice. I put AGL instead of ALG. There we go. And all we have to do now is print out our eigenvalues like that. And you'll see our values are going to be 1. And yeah, that's essentially it from the NumPy side of things. Don't make the same mistake I did and accidentally type AGL on here. I don't know why I was doing that really fast, but make sure it's ALG. And really to define it, again, there's 2 ways. Identity, I prefer using identity. If you want to use I, go for it. I just like using identity, right? And it's square, so put in whatever you want on that side of things, right? It's going to be the same length each side. And remember, this diagonal from left to right will be 1. Everything else will be 0. I showed you matrix multiplication. Order does not matter. With this side of things, with the identity matrix, and we cover the determinant, which will always be 1, inverse, which will always be the same, and then eigenvalues, which will always be 1. Hope you guys enjoyed this video on the identity matrix, and you found some value from it. Make sure to subscribe to the channel. We're trying to upload at least 2 to 4 different data science focused videos every single week. Now, I'm still developing a linear algebra playlist, but I'll link a few videos down below, and the playlist will be right over here.